Hola amigos! Today I'm back with a Niagara tutorial where we're going to look into how to apply rigid body dynamics to our systems, or to put it in other words, how to implement particle collisions. As most of you already know, in Unreal, particles in a system don't collide with each other, and this is also true for most other engines. The reason is that in order to support hundreds of thousands of particles, these are treated just like points, therefore they don't have an actual geometry that we can calculate collisions against. As this example here shows, we can instance meshes on the positions of these particles and using methods like signs distant fields, approximate a collision against other objects in the SDF. Adding some fake rolling motion based on their velocity can make the effect better, but once the particles start to clump together, it becomes pretty obvious that they are intangible. However, let me enable this script that I made, and now particles will start colliding with each other and accumulate and fill this container until eventually they overflow. There we go. In this other example, particles are attracted to the system's origin, but they are also colliding with each other, creating this cool-looking particle blob. There's also some curl noise to make these motions more interesting, but otherwise it is a very simple emitter with just a couple forces applied. And now, before we get deep into these Niagara systems, let me quickly jump into Photoshop to explain the two techniques that make this effect even possible. We'll start with the concept of neighbor grids. I'm going to use a 2D example to illustrate this, but it will work the same way once we add a third dimension. Let's say that we have a system with a few particles and we want to solve the collisions between them. I mark in yellow all those particles that intersect others to see them better, but obviously Niagara can't do that. So the first step is going to be to find out which particles need to be moved out of the way. A brute force approach would be to iterate through each particle and for each one get the distance to everyone else. If the distance is less than twice the radius, then we have a collision. So for example, we would start on this one and check the distance to this, and so on. And the problem is that this would quickly get out of hand because the number of calculations grows exponentially. With n particles, we would have to do n squared calculations or n squared checks. So just 1,000 particles would be 1,000,000 operations. And that's where the neighbor grid comes in. Let's set a neighbor or a 2D grid on top of our system. We are also going to assign IDs to our particles so we can identify them by index. So for example, we have 1, 2, 3, 4, 5, 6, etc. Next, we're going to inject these particle IDs into the grid cell that each particle occupies. So let's see how it will work. These cells would be empty and they get no data injected, and this cell here would get the ID 1 injected into it. Then we have more empty cells. This one gets the ID 3, and this one, for example, gets both the IDs 4 and 5. This one would get 3 IDs, this one another 2, all these ones are empty, and so on. And the good thing about this is that we can do these operations in a single pass through all the particles. So it's just n number of passes of calculations, because we know where the particles are, where the grid is, and we can convert very easily between their coordinated spaces with just a bit of simple math. And to understand why this is going to be useful, let's stop here for a moment and think about the grid cells. We can label them in a couple ways. First, with their axis coordinates. So this would be the x-axis, the vertical one is the y-axis, so we have 0, 0, 0, 1, or 1, 0, 2, 0, etc. And the same for the vertical axis, so this would be 2, 2, this would be 5, 4, and so on. And another way to label them would be to use a linear index. So starting at 0, 1, 2, 3, 4, 5, so on until we get to n minus 3, n minus 2, n minus 1, and n number of cells. And this is pretty cool, and we're going to actually use both indexing systems later on. But the important thing is that a grid, just by definition, contains spatial information. In our case, that means that we can check adjacent cells without having to traverse the entire grid. So, for example, the cell below this one would be, if we're using the x and y coordinates, this would be x stays the same and y plus 1. And if we're using a linear index, this cell would be the index of this cell plus the number of cells in a row. So again, pretty simple math. So let's say we want to check collisions for this particle. We can check all the adjacent cells and just check the particles contained or whose IDs are contained in these cells. So to check one collision or collisions for one particle in this case, instead of doing one check for every other particle, we would need to just check about 10 of them. And this is going to immensely reduce the number of calculations that we have to do. And that's it for neighbor grids. A couple things to keep in mind when using them. First is that the size and resolution of the grid will impact the results. And this is one of those cases where higher resolution is not always better. And the second one is that in order to improve performance, we're going to limit the amount of neighbors that we inject into the grid. Once the collisions start resolving and particles move away from each other, that won't be a problem. But just keep in mind that it's another parameter that we will have to tweak to get the best results. Okay, so in short, neighbor grids allow us to limit our distance checks only to nearby particles. Now we can move on to the second part to see what are we going to do when we find a collision. Let's say that we have two particles of different sizes and we have determined that they intersect because the distance between them, which is d, is less than their combined radius values, so r1 and r2 respectively. Our simplified collision solution is going to be to simply push them apart in the direction of this vector d. To account for size differences, we'll move each particle proportionally to its mass. In this case, the smaller particle will move about twice as much as the larger one. So they will end up here and here. In the case of a particle having multiple collisions in a single pass, we will also have to average the results by dividing by the number of hits. But in a nutshell, this is it. You can also expand this method by adding more complex collision behavior, friction, support for immobile particles, and other features, but those are going to be beyond the scope of today's tutorial, and besides, they should be easier to implement once we have a good grasp of the basics. And now, without further ado, let's go back to Unreal and start working on these particle systems. Okay, let's start by creating a new material, which we can call material simple particle color. And let's also create a Niagara system from a selected emitter and select the empty template. Click the plus icon to add one of them and finish. And we can call that Niagara system RBD tutorial. Let's save both of them. And let's start with the material because that will be the simpler of both. We are going to use this material to debug our neighbor grid and our collision, so we just need the particle color. So let's select the parameters first and search for Niagara, and then select Use with Niagara Mesh Particles. Now we can add a particle color here and connect its RGB output to the base color. Now we can apply and save and close this window. Now let's open our Niagara system. Let's start making some changes. Before we start working on the collisions, let's begin with a more simple particle system. So select our emitter and we'll start by changing the name, something like RBD. And starting from the top, let's go to the properties and change the sim target to a GPU. Same, we get this warning about the dynamic bounds, so let's change that to fixed and change this to maybe 1000. There we go. From -1000 to 1000. And finally, let's also check the requires persistent IDs. We need our particles to keep their ID through the entire simulation. Going down, let's keep the life cycle and scalability determined by the system. We'll change that in a moment. Then on the initialized particle, let's just change the mesh scale to uniform and set this to maybe 10 units for now. Next, on the particle state, we don't need our particles to die, so we can uncheck this. And let's replace this sprite renderer by a mesh renderer. So search for mesh renderer. And here we want to change this mesh by one that you can search for 1 unit and search for 1 unit sphere, which is in the RTools render to texture meshes folder. Now we can also override the material on this mesh and search for the material that we just made on the content browser and drag and drop it to the explicit material. Now we need some particles, so on the emitter update, let's add a spawn burst and add, for now, I don't know, 100 particles. And let's also give them a location. So on the particle spawn, let's do a shape location and maybe a sphere 20 units in diameter. Maybe we can make this, like, keep them at 1 unit and see how it looks. Okay, we have a bunch of tiny spheres. Let's reduce the shape location to 5 units. Okay, now we have a bunch of spheres and many of them are intersecting. Perfect. And we don't have any forces, so the particles stay there and they don't die. Now let's go back to the system properties and start making some changes here. Let's go to the system state and change the loop behavior to once. Now, we need a neighbor grid, so let's create one. On the system spawn, let's add a new set new existing parameter, and here you click the plus icon and search for neighbor. And we have this data interface called neighbor grid 3D. Perfect. Now we are going to initialize this grid and give it some parameters. So let's create some user parameters so we can change those easier. Let's start with a vector, and this is going to be our grid size. Let's give it a default value of maybe 1000 units. Perfect. Now let's create an integer and call this one grid resolution X. I'm going to copy this part and then create another integer for grid resolution Y, and finally another one for grid resolution Z. Perfect. Now we need one more to override this max neighbors per cell. So let's add a new integer and call this one max neighbors per So now for the default values, let's start with 16 for the resolution and maybe 8 for the max neighbors. Perfect. Now we want to apply these user parameters to our neighbor grid. And since one of the properties of this grid is the position, and we might want to move the emitter and obviously the grid along with it, we need to update these parameters on every frame, which means that we need to do that on the emitter or the system updates, not on the emitter or system spawn. So let's go to the emitter update, for example, and add a new scratchpad module. And we can rename this to initialize neighbor grid. Now let's start by getting our grid. So we can go to the parameters tab, click on active overview, and here find our neighbor grid and just drag it to the map get. Now we can make a bit of room here on the side. And if we drag from the neighbor grid and search for set, now we have one of the functions called set number of cells or set num cells. Now let's put this into the chain. Perfect. And now we can drag from these inputs into our map get. And that's going to create new inputs for this function, named as the inputs on this set number of cells. So just drag into the plus icon for number of cells X, Y, and Z, and also for the max neighbors per cell. Great. Now let's add also a new vector and call it grid size. Great. Now if we hit apply and go back to the system overview, in our initialize neighbor grid module, now we have all these parameters exposed. And we can go to our user parameters tab and drag the grid size onto the grid size, grid resolution X to number cells X, same for Y, Z, and maximum number of neighbors per cell parameters. Perfect. Let's go back to our scratchpad and continue. Now we need to create a new parameter or new variable that is going to contain or to hold the matrix that we will use to transform from the simulation space to the unit space, that is from 0 to 1, that corresponds to the grid. So let's start by making a bit of room here and adding a new matrix to the map set here. And we can call this sim to unit and right click on the local icon and change the namespace to emitter. So we have now emitter.sim2unit. Now to build this matrix, we basically need to combine the grid size and the position of the emitter to change that into a centered 0 to 1 scale. So let's start with the grid size. We can add a divide and then right click on the first input and convert numeric to float. Now we can connect the grid size to the second input. It will automatically change to a vector and then change this number to 1. So we have 1 divided by grid size. Now we can right click on the result and convert this to a vector. Great. Now from here, we can drag the output and search for make a scale matrix. Great. Now we have the first of our 3 matrix that we need to combine in order to make our final sim2unit. For the second one, we need the position of this emitter. So let's click the plus icon, search for owner, and add the engine owner position. Now we could operate in large world space coordinates, but everything is easier if we convert this to a vector first. So drag from there and then search for position to vector. Great. Now, in order to convert this vector to our usable matrix, we can do a couple things. We can multiply this vector by -1 and then create a translation matrix, or we can create our custom HLSL. It's pretty simple. Let's call this one this T. Remove this comment to make this window smaller, and then drag from our vector to our first input. We can rename this parameter to T, and then click the plus icon to add a matrix output and call this one out matrix. Now I have a bit of code that I'm going to paste here, but it's very simple. Basically, our out matrix output parameter equals a new matrix, a float 4x4, which the first 3 rows are 1 0 0 0, then the second one 0 1 0 0, and the third one is 0 0 1 0, and the fourth one, instead of being just 0 0 0 1, which would be the next on this pattern, is -t, 1. So we have the opposite of this vector, 1 as the fourth row of this matrix. And again, you can do this with just multiplying this vector by -1 and then using a make transform matrix or translation matrix. Now let's multiply these two together. So let's drag from here and search for multiply. And we need this multiply matrix times matrix. And make sure that the transform is the first input and the scale is the second one. Great. Now our transform matrix almost works. It converts from the simulation space to a 0 to 1, but this 0 to 1 is now centered on a corner of this grid. So now the position of the emitter, so the center of this blob of particles right now, it's in one corner of the grid. So we need to apply a second transform matrix or translation matrix. So let's search for make translation matrix, and this translation, let's set it to 0.5 on the 3-axis. And 0.5. So now that this will center our grid, so it's centered on the position of the meter. So to combine this with our previous result, we just need to multiply these two matrices again. So drag from here again and search for another multiply matrix times matrix. And on the first input is again the result of the transform times scale, or the translation times scale. Sorry. And on the second one is the result of this times and not the second translation. So this is the world translation or local, depending on how the emitter is set, and this is the local offset of the grid. Great. Now we just need to connect our final result to the sim to unit parameter. Now to make sure that everything works, we can click apply, and if we don't get any errors on the Niagara log, everything is working fine. Probably we'll have to test it in a moment, but for now we can compile, save, and go back to the system overview. Okay, so this first scratchpad, basically what it does is updating the neighbor grid, and if our math is correct, making sure that it stays center on the emitter position. The next thing that we have to do is to inject the particles into the grid. And we need to do that after applying all the forces and solving the velocity, so let's add a new stage by clicking on this icon and add a generic simulation stage. Now here we can change the name to something like Populate Grid, and we can leave the parameters as default, but we need to add a new scratch pad. Let's call this one Populate Neighbor Grid. Okay, to inject these particles into the grid, first we're going to need the grid. So let's go to our Parameters tab, and same as before, click on Active Overview and drag our Neighbor Grid 3D into the map get. Now we want to add these particles to the grid, and luckily for us there's a function that does that, so we can drag from here and search for Add Particle. Now let's connect this into the execution chain, and let's look at the parameters. So we have our index x, y, and z, and then particle index. So this function will write into the specific cell of the grid, defined by these coordinates, the index of this particle. So for the index, we can just drag and search for execution index. Great. Now for the x, y, and z coordinates, let's drag from the neighbor grid again and search for unit. And we have this unit to index function. Let's make some more room, give this more space. Now we can connect the outputs of this function, x, y, and z, but this requires a position vector in the unit space. So let's drag one more time from the neighbor grid and search for simulation. And we have this simulation to unit. Now we can connect the output of the simulation to unit into the unit to index. And the last thing that we have to do is fill these two other inputs. The first one, the simulation, is just the position. So let's search for position and add the particle's position. Now we need to convert this into a vector again, and we can just drag from here and it will add this one of these conversion nodes, or we can also search for the position to vector function, which should be a bit more precise. And for the simulation to unit transform, well, that's exactly what we calculated in our previous scratch pad. So we can go to the active overview and the parameters tab and expand the emitter attributes, scroll down and search for our sim to unit matrix. Now we can drag it to our map get, and from here just connect it to our simulation to unit transform on this simulation to unit node. Now to make things a bit easier to read, we can double click on the connections and move these nodes around. We can also add one here and then maybe reconnect from there to here. So now it's a bit more clean. Now we hit apply and compile. We don't get any errors, but it's still hard to see if the particles were added. Thankfully, this add particle has a success output that we can use to know if the operation was done correctly. So drag from the success and add a select if node. Now by default, we have just wildcard on the inputs and the output, but we want to set the color of these particles. So first let's add this to the map set. So search for color and add a particles color. Now if we drag from this side into this wildcard, it will convert the wildcard to a color. Now we can say that if the particle was added to the grid or injected, let's make it green. If it failed, let's make it, yeah, this kind of orangey reddish. Now if we hit apply, we should have a bunch of green particles, and there we have it. Now let's test it on the viewport and see if it really works. Let's add one of our particle systems, and the particles are tiny. So let's go back to our system overview, and for now let's make the particles just bigger, and later on we'll use a nicer or more fun way to calculate the size. So let's make 10 and maybe make this size of the shape location sphere like 100 units. Cool. We can increase that to 200 maybe. Great. Let's compile and save and go back to the viewport. So now we have our particles, and because they don't have applied any forces or any dynamics, if we move the emitter, now the grid is still center of the emitter. So if we move it 500 units, now we start to lose some of the particles. So this is working, and the same if we move it up. Great. So at least for now, both of our Scratchpad modules seem to be working nicely. Let's go back, and now let's move on to the collision part. Before we add another stage and another Scratchpad, we need to make some changes in our emitter. The first one is that on the emitter spawn, we're going to create a new particle reader. So on this stage, add a new set new or existing parameter. Click the plus icon and search for particle attribute reader. Now we have a couple warnings, but before that, let's change the name of this from particle attribute reader, which is very long, to just particle reader. Now the warnings are because this emitter name is still not set, and we need to read particles from itself. So in our case, this is named RBD. So let's name this RBD as well. Great. And now the warnings disappear because it found the emitter. Let's keep going down. And on the particle spawn, let's first go to the initialized particle, and I'm going to make a couple changes. So instead of setting the mesh scale uniformly, I'm going to set it in a different module. So let's set for now to unset, and we're going to instead use mass. So change this to a random, and maybe something, yeah, like between 5 and 10 is good. Now our particles are tiny, so they are all 1 unit in size. So let's, on the particle spawn, search for calculate size, and we have this calculate size and rotational inertia by mass. Now we need to check the calculate mesh scale, because we are going to apply this to our mesh renderer, and we know that our model is 1 unit in radius, so the model dimensions is 2 on each axis. Now we can change the density by material type to a styrofoam if we want bigger spheres. Maybe change the mass modulation to 2 to make them heavier. And now we can change maybe the shape location to increase the sphere radius, maybe 200. Yeah, something like that. Now for the collision, the last thing that we need, we have the particle reader, but we need to know the radius of each particle. So we have the size, but we need to apply that or save that as a value that we can use in our scratch pad. So on the particle spawn stage, let's add a new set new existing parameter. And add a float, and let's name this collision radius. Now, instead of setting this to a fixed value, let's search for calculate, and we have this calculate particle radius. And we need to change the calculation type to mesh, because that's what we're using, and also update the mesh dimensions to 2 on its axis, just as we did here for the calculate size. Great, so now we have scale our particles up and down based on their mass. So we have bigger particles and smaller ones, and from that value we calculated also the collision radius, and we stored it in a variable that we are going to use in our next stage. So let's click on the plus stage button, and after the populate grid we're going to have a new stage. Let's change this to maybe RBD collisions. Now let's add a new scratch pad to this RGB collisions stage. So, new scratch pad module, and we can call this one maybe RBD collisions. This is going to be the most complicated, so let's start with the map get. So we'll need, as usual, our grid. So let's find it in our parameters, active overview, and drag here. And then from the emitter, we're going to need our sim to unit transform. And where is it? Our particle reader that we created earlier. Now from the particles, we need the position, we need their mass, and we need their collision radius. Perfect. And on the map set, for now, let's just set the position. Great. Now let's add a custom HLSL, and we can call this one RBD maybe. And let's organize this, make a bit of room, and let's connect all these parameters as inputs in our function. The only thing that we'll have to do is get the position and first transform it into a vector. So position to vector. And now we can drag all of this into the plus icon. And also I'm going to rename this one to just grid. So it's a bit shorter. And we can keep the rest of the names as default. I'm going to rename this one to position, and then we can keep going, mass, collision radius, and let's also, as we did before, find the execution index. So search for execution index and drag this result to create another input, and we can call this one exec index. Perfect. Now here in the output, we need to create three output variables. One is going to be a vector, which we can call out position. The next one is going to be an integer, and we can call this one neighbor count. And finally, a boolean, which we can call collided. Now, this output, first one, out position, is going to contain the final position of the particle after we push it out of the way of the intersection. The next one is going to contain the amount of neighbors that collided with this particle on that frame. And the final one is just a boolean to know if particle has collided in that frame or not. Now we can convert this back into a position with a vector to position. Oh, there we go. Vector to position, and then connect this to the output. And then for the other ones, we can start dragging them here, and then we need to change this namespace to be particles. So just right click on the local icon, go to change namespace and select particles. Okay, now we are set up to write this code. I'm going to write it in a different notepad or WordPad session so I can make the font a bit bigger, and I'll be right back. Let's actually add the code one step at a time. This first part is going to initialize our output variables. So in case everything else fails, our return position will be the current position of the particle, and will return no collisions. So collided equals false and neighbor count equals 0. Next, we need to add a precompiler instruction that basically will ignore everything inside this block if we are running a CPU simulation. The reason is that neighbor grids are only compatible with GPU ones. So add this block, if GPU simulation, and at the end of your code, this end if. Next, we're going to initialize a couple of variables. The first one, I'm going to make this a little smaller. There we go. The first one is going to be this index offsets, which is an array of integer 3, so vector 3 of integers, of 27 elements, and they are basically all the different offsets that we need in order to get all the neighbors of a cell in 3D. So as you can see, this first set of 9 is the -1 on the first axis, and then -1, 0, and 1 on the second one, and the third one alternates between -1, 0, and 1, -1, 0, and 1, and so on. Then the second one repeats the same, except that in the first column we have zeros, and in the third one we have ones. We could also do this with 3 different for loops, but this is a bit more efficient. So I'll go slowly, but feel free to pause the video and copy these values. Okay. The next thing that we need is to initialize our return position offset. So this is going to be a float 3 called final offset vector, and its initial value is 0, 0, 0. Next, we're going to initialize a few more variables, but this time we're going to use functions that we're going to call on the grid. So let's start with the number of grid cells, so the resolution of each axis. So it's an integer 3, so one of these sets of 3 integers, called numCells. And to initialize this, we're going to call this function from the grid. So grid.getNumCells, and then this function, instead of returning the value, it requires three parameters where we're going to store the number of cells on each axis. So in this case, we're setting the three axes or three values on our new integer called numCells. So grid get numCells x, y, and z. Perfect. Now we're going to do the same with a couple more, but before we're going to do that, let me go back to Unreal for a second. So if you are typing this directly on the HLSL editor, if you start typing grid, for example, dot, you have this select autocomplete options. And then you just press the number of the function that you want to call, and it will create this function for you and will tell you what you need to put on this on these parameters. That's how you know which functions are available for each of these inputs. You can also right click on this and here, data interface function HLSL. You have all these functions and you can copy them into the clipboard. So let's continue, and next we want to get the maximum number of neighbors on each cell or per cell. So it's an integer called max neighbors per cell. And to set that value, we call this function grid.maxNeighbors per cell, and the parameter is this integer. Cool. The next one that we need to get is the position of the particle in this unit space. So in the space of the grid, in a 0 to 1 coordinate. So we create a new float3 called unitPos. And to set this value, we call this simulation to unit. And the parameters for this function are first the position that we want to convert, then the transform matrix, which we calculated earlier, and then the parameter or the variable where we're going to store the result. So this one. Perfect. And finally, we need to convert this unit position into our XYZ coordinate space. So we're going to store the position of this particle also within the grid. So it's called index, it's an int 3. And to set that value, we call this unit to index. And the first parameter is the unit position, which we calculated here. And then the other three are the three coordinates that we're going to store. And we're storing them in this parameter. Great. Now we're going to move into the important part of our loop. First, we're going to iterate through our cells. So let's add a new for. Close the brackets. And this one goes from 0 to 27. And that's because we're going to iterate through all the elements in this array. So these are offsets. So we're going to apply on each pass of that loop one of these offsets to our current index. So we're going to get the neighbor cells that way. So for xxx, or could be xyz, equals 0 to 27, let's do a bunch of things. First, we need to know what is the index or the xyz coordinates of the cell that we are going to test. So this could be like this. So first we create a new variable called index to use. It's an integer 3 and is the current index, which we calculated here. plus whatever element of the array we're using as the offset. Now, we don't want to test cells that are outside of the grid, so let's ignore all the cells that are outside the boundaries. So we can do that with an if check. Let me close the bracket. So if the coordinate of the index to use on the x-axis is bigger than 0 and lower or bigger than bigger or equal than 0 and is lower than the number of cells in that axis, and that repeats for all three, x, y, and z, then we know that that cell is within the boundaries of the grid and we can go testing. So the first thing is going to be convert this index, which is right now on the XYZ format, into a linear index. That we're going to call another of these grid functions. So we create a new integer to save this value called linear index. And we call this index to linear function. The first three parameters are the x, y, and z values that we want to use, and which are these ones here. And then the fourth parameter is the variable where we're going to store the result. So now we know the linear index of the neighbor cell that we're going to test. Now we know we want to check if there are particles in that cell. So let's get the number of particles. Same, calling a function from the grid and storing the result in this neighbors in cell variable. So the function in this case is get particle neighbor count. The first parameter of this function is the index or the linear index that we want to use, and the second is the variable where we're going to store the result. So now we know that in that neighbor cells there might be a few particles. Let's iterate through those. We'll do that with another for loop. Make sure that I close all the brackets so don't forget any. Cool. This for loop will go from 0 to the number of neighbors in cell. So inside that loop, first we need to get the linear index of the current particle. So we create a new variable to store the result of this function. So it's called neighbor grid index to linear. And the first three parameters are the coordinates that we want to check. And then the index of this particle, which we're getting from this index, where we are iterating through these neighbors in cell. And finally, the variable where we're going to store the result. So now we know the linear index of this cell or this particle. Now, we need to get the ID of that particle, so the execution index of that particle. We do that with another grid function call, in this case, get particle neighbor. So this one requires the linear index. Again, we get it here. And then as always, the variable where we're going to store this result. So we're iterating through the particles in one of the adjacent cells, and we're getting the ID, or the execution index, because they are permanent, they're valid as IDs of that particle. Now we need to make sure that we don't test against itself or test against invalid results. Yeah. So if this ID that we just calculated is equal to the execution index of the current particle, or this ID equals -1, then continue. So that will skip the rest of the block and we'll move to the next iteration in this for loop. So we skip this particle because it's either invalid or is the same particle that we are originally testing against. Now we're going to use the particle attribute reader. And for that, we're going to need to create a Boolean to store the results of the read operation. So this is part of the reader particle attribute reader operations. So we create just a new bool called read result. Okay, so let's first read the position of the particle whose ID we just got here. So we cannot do just a particle's position because that's the position of the current particle. And right now we need to know the position of the particle in this adjacent cell. So we're going to, this is slightly annoying, the tabulation. Okay, so first we're going to read the position, so we need a float 3 called other position, so the position of the other particle. And we're going to do that by calling a function from the particle reader. So it's called get position by index. So particle reader dot get position by index, and first between these lower and higher than symbols, we need to type this attribute equals, and then we need to pass the attribute of the particle that we want to read in a string form. So between these quotes, we need to type position. And we are using this function called get position by index. So the parameters of this are the ID of the other particle, so it's this one, then the Boolean that is going to store the result of this operation, and then the variable where we're going to store the result. So now we know the other position, or the position of the other particle, and we can also continue and skip the rest of the loop if this particle or if this read operation fails. So if we are not sure about the position of the other particle, then just skip it. And now we're going to do the same with the radius of the other particle. So let me copy this. Okay, so same as we did here, we create first a new float. So here we created a float 3, and we're using get position by index. Here we're creating just a regular float called other radius, and instead we're using the function get float by index. Note that these are not the same. it also you need to still pass the attribute name in a string form. In this case, we need to get the collision radius of the other particle, but the rest of parameters are the same. First, the ID of that other particle, then a boolean for the results, and then the variable to store the result. And same as we did here, if that operation fails, then just continue or skip the rest of that calculation. Okay, so a quick recap of what we've done so far. We have a particle, and we know which cell in the grid that particle occupies. Next, we're iterating through all the adjacent cells to that one, and within those adjacent cells, we're finding how many particles are in there. Now, we find some particles, and then we determine that they are valid ones to test, and now we know the position and the radius of those other particles. Now we're ready to compare the distance between them and the radiuses, or the radii, and we can determine if there's indeed an intersection between them or not. So first we need to know the distance and the direction or the push direction between both particles. So let's start first with the direction between both particles, and that's just subtracting both positions. So the position of the current particle minus the position of the neighbor particle will give us a vector that connects both of them. Now, to know the distance between those particles, we just need to get the length of that vector. So we're storing that in a new float called dist, and that is the length of this vector called push direction. Now we need to know also, because it's going to be useful later, the normal or the normalized vector of this push direction. And for that, we can either use a normalize function and normalize this vector, or since we already calculated the length of that vector, we can just divide this vector by the distance. Great. So now we know the distance between those two particles. And because we also know their radii, we can calculate the overlap between them. So a new float called overlap, and that's equal to both of the radius values combined minus the distance. So if this value is bigger than some factor or bigger than 0, then there's some intersection. So let's do that. So if the overlap is bigger than, in this case, 0.5, but we can reduce this value, I don't recommend having it at 0 because sometimes you get too much vibration between particles, but a value of 0.5 or 0.1 is usually pretty good. So if there's an overlap, if these two particles are intersecting, then we need to do a couple things. First, we're going to increase the neighbor count. So, hey, now we have one collision that went through all the checks and is indeed intersecting. So let's increase this total number of neighbors, which if we scroll all the way back to the top, remember it starts at 0 on every iteration. So if that happened, we also can set our collided boolean to true. So collided equals true. Now because now we know that there is an intersection, now we can also read the mass of the other particle. So same as we did before, with this radius and position, let's read the mass of the other particle. And we don't have to do this if we don't have an intersection, and that's why this mass is inside this if. So we create a new float called other mass, or the mass of the other particle. And in this case, we're also using the getFloatByIndex function that we use here, not getPosition or getVector. So getFloatByIndex, the name of the attribute is, of course, mass. And we are still using the same ID of the other particle, storing the results in the same Boolean, and storing the results of the read operation. Storing the results of the read operation on the same Boolean, and storing the result of the particle mass attribute on this float. So now we know the mass of both particles, and we know that they're intersecting. So let's find out what's the percentage of mass that the current particle, not the neighbor one, represents. So we create a new float called mass percentage, and if we take the mass of the current particle, the one on the main loop, and divide it by the sum of the combined mass of both particles, then we have a 0 to 1 value that it represents the percentage that this particle occupies of the total. Now we are going to do that because we want to use this to scale this the vector that we are going to use to push those particles away. So the final offset vector, which we initialized all the way outside the loop here. So this final offset vector, go back, is plus equals. So we are increasing it on every pass of the loop where there's a collision. We are increasing this vector a little bit. So plus equals, first is 1 minus the mass percentage times the overlap. So times how much these particles overlap, times the vector of the direction of the push in the normalized vector. So the vector that measures 1, then we are scaling it by the amount of overlap, and then we are scaling that again by 1 minus the mass percentage. The reason why it's 1 minus the mass percentage and not just the mass percentage is that we want to push away further away the smaller particle. So a bigger particle will have a lot of impact on a smaller one, but a smaller one won't push a bigger one. Okay, so after all this, we just I have the overlap closed. Yeah. So after all this, we have this vector, which it accumulates when we test over all these neighbor cells. So outside all of this loop, so once we finish testing all these cells, we can check if there was a collision. So if collided, then add a closing bracket. So if this collided, let's increase our position by this vector. So if collided, out position, and same as here, we are increasing our current value, and our current value, it's again all the way at the top, and we are started with the current position of the particle. So we're taking that current position and we're offsetting that. So plus equals this final offset vector. You can ignore this one times. Final offset vector, and then we are dividing that by the amount of neighbors that this particle collided with. The reason is that we want to average all those vectors. Otherwise, each particle that this one collided against will push at maximum strength in one single frame, and we would have particles like basically exploding everywhere. And that's it for this code. We can now copy everything and paste it into our HLSL window. So let's go back to Unreal, and I already pasted it here. But if you hit apply and compile, hopefully you don't get any errors. If you get any errors, just make sure that all your variables are named correctly, that these inputs match the names that you're using for them later, and same for the outputs. And yeah, feel free to rewind the video and go back to the code if you need to make sure, double or triple check it. Okay, so now we can go back to the system overview, and if we hit play, oh, it's hard to see, but these particles start intersecting and then just push each other away. So just to make this a bit more obvious, let's reduce this shape location. So let's reduce the radius to maybe 100. Let me make this bigger. Yeah, so the particles don't really have any forces applied, so on the particle update, there's not really anything happening. But if we hit play, they are still moving away. And if you watch closely, we have now a few particles red, and that's because the number of neighbors is not high enough. Like this particle here, it's on a group that has more than 8 other particles, so it didn't fit on that grid cell. Now, as you can see, that's not really a problem, because as the algorithm iterates, it pushes that particle away, and then it's no longer has that many neighbors, and it kind of fixes itself. Now, one thing that you can do is go to the RBD collisions stage, and on the generic simulation stage settings, increase the number of iterations. Right now, this is pushing the particles one time, and then seeing what happens, but let's increase that to maybe 5. So it resolves a lot faster. And the red particles disappear also a lot faster. So we don't have as many. Now let's start making this a bit more interesting and adding some forces. Let's start with maybe a point attraction. So point attraction force on the, oh sorry, I added it to the particle spawn. It should be on the particle update. And now we have the issue where we need to solve forces and velocity. So let's click on fix issue, and it will add for us this solve forces and velocity. Yeah, so this force right now is very subtle, so let's increase this attraction strength to maybe 1,000. And you can see that now our particles are exploding because the attraction radius is still very small. So let's do a crazy distance. And now we have a lot of noise. And one of the issues that's happening here, or the issue that's happening here, is that after we modify the position of these particles, we are not recalculating their velocities. So on the RBD collision stage, let's add a search for accurate and add and calculate accurate velocity. Now it will complain because it says that you need the solve force and velocity, and we don't really need it, because the important part of the forces and velocity is to recalculate the positions of the particles. And we don't really need that. We are doing that because on this RBD collisions stage, the only thing that we need is to recalculate the velocity. So we can click the dismiss issue because it says here, I know what I'm doing, and I do. So dismiss issue and see how it behaves now. And now it's a lot more stable. And we have particles moving around because they are all trying to get to the center, and smaller particles are being pushed away by the bigger ones, so we get a little bit of movement. Cool. Now let's make this even a bit more interesting. One thing that we can do is add some rolling to these particles. But right now, if we do it, well, we won't see anything, but because they are just a flat color. So first, let's go to this mesh render, and I'm going to just change this for some other material, whatever has some pattern to it. So let's do something that is easy to see, like this color grid. And now we have all these particles, and it's very clear that they are not really rolling around. So on the particle update, let's add an update mesh orientation. So instead of having a rotation rate, let's use a rolling orientation. And now it has a warning, and because it says that you haven't selected, or I haven't selected a mesh render. So let's go here and select our mesh render. And now it doesn't complain. And we don't really have to change anything here. I think it's fine. We can hit play. And now all these balls are rolling around, and the behavior is a bit more believable, more physical. Cool. Let's now maybe add a bit of noise. So curl noise force. And let's look at the parameters. Yeah, let's increase the strength, maybe 2000. And the frequency, how big are these? Yeah, maybe something like very small, like 2 or 3. Okay, now we have a bunch of noise, and maybe we can even pan this noise so they are not always moving in the same way. Maybe minus 0.5. Cool. And now it's about a lot more organic. Now the last thing that we can do to prevent some of those particles, sometimes on those collisions, if there's still a lot of collisions against a very small particle, sometimes you can get those flying away really fast. So let's prevent that with a bit of drag. So we can add a little bit of drag here on the particle update. And now we don't have, even at the beginning, those particles flying away that much. Cool. And if we look at the one in our scene and we activate it, we can move the emitter around. This follows it. And it's a pretty cool, it's like a ball of ice almost. Pretty fun. Okay, so hopefully you've been following this tutorial and you have something that behaves more or less like this, but maybe not. And there's a few possible issues that you might be having here. So the first one is obviously the code. You might have coding errors here, and usually the Niagara log will give you a good indication of where to start looking. It will give you the line that is failing on the compiler, and usually a message that indicates if you have a type mismatch. So maybe you're using a float 3 where you should be using a float, or you're using a get position when you should be using a get float. Problems like that. And those are usually easy to debug. The next thing that can happen is that your particles behave in weird ways, maybe very erratically, or they look like they skip frames, or they move instantly out to their destination and they don't move smoothly. And that's usually because of problems on the grid resolution or the grid size. So both things combined, this resolution and this grid size, will determine the size of each cell on this grid. So let's see what happens if I increase this to a really high value, like 64 by 64 by 64. Now they're exploding, and that's because on most of these collisions are ignored until the particles are really inside each other. So imagine now these cells are really tiny because the resolution is very high, so each cell is very tiny, and it won't catch neighbors intersecting with these particles until they're really, really close, which means that all these forces pushing these particles away are really scaled up. And if it's very small, if the resolution is very low and the grid cells are very high, you will be skipping collisions altogether, because you won't have usually enough neighbors per cell to cover all the particles that would be in one cell. And also, it's less efficient because you still do a lot of checks. So play with these values, combine resolution, grid size, and the size of the particles until you get a simulation that behaves in more or less a smooth way. Now, the next thing that can happen is that maybe you're trying to add some initial velocity. So let me go back to the stage or to the scene and show you this other particle emitter. So I have this other emitter here that just spawns a bunch of big particles for a few seconds. And let's open it up. Now, as you can see, I have an add velocity, and I have a pretty strong velocity, 500 units in the x-axis. It's on the local coordinate space. So in theory, these particles should be moving in that direction as they spawn. But they are not. And the reason why that's happening, as you can see here, they behave like popcorn, is because they are colliding in the first frame. So as they are spawning, they are colliding. And there's a couple ways to avoid that. If you can still tweak your simulation parameters, you can reduce the spawn rate. So if I just change this to 1 particle per second, now when we activate it, our particles are indeed going towards that wall. But maybe you want a higher rate. So another thing that you can do, let's set this to 20, is to increase the shape location radius, or spawn your particles in something like a grid, or basically spawn your particles farther away from each other to guarantee that they don't collide. So let's set this to 300 units. That's a lot. So now if we activate it, most particles, they still some collide, and once this starts filling, they don't really have that velocity. But at least the first ones, they go like that. And finally, the last thing that you can do, let's reduce this sphere radius back to 25, is to reduce the size of these particles. So back on the initialized particle module, you can change the mass to maybe like something between 1 and 5, 1 and 3, to have really small particles, and that way they should not collide. Oh, we can maybe increase the the radius a bit, reduce the spawn rate to maybe 10, increase the velocity to 750, increase this radius to maybe just a bit more. Try again. And now we have our particle host. So as you can see, you can tweak several of these parameters to avoid this initial collision, but it depends on what is your use case scenario. Now, if another thing that can happen, especially if your particles are affected by gravity and forces, is that those, because our neighbor grid is still attached to our particle emitter, which is here, if the particle emitter gets too far away, these collisions will stop being calculated. So right now it won't be a problem because they are already resolved and these particles are already de-intersected. But if we get far away, now we have some collisions here, and if we move the emitter close again, we can see how they start resolving. So again, yes, something else to keep in mind that is that the grid, the neighbor grid is attached to the emitter and is moving with the emitter, so just make sure that any particles that are too far away are not important or not going to be seen. But I think that's it for the most common problems that you might be experiencing if you follow this tutorial. And that's gonna be all for this tutorial. As a couple bonus ideas of what to do with this effect, you could use the boolean for collision or the number of colliders to do things like flash particles that collide or tint particles based on the number of neighbors or other abstract effects like that. In terms of performance, well, right now this is running within the editor and capture, open, a bunch of other things at 120 frames per second, and the entire simulation with, I think it has 750 particles and 5 iterations on the collision solver. It's running, I think it takes 0.43 or 0.45 milliseconds to run. So performance is not bad. You can of course increase these numbers and have more iterations to eliminate some of the smaller vibrations that you can see, or tweak the numbers on the grid resolution to fine-tune the calculations, but at some point you might start to get into performance problems, especially if you get 100,000 particles and they are really tiny and there's a lot of collisions with a lot of cells in that grid. Maybe you can start to get into the 1, 2, or maybe even 3 millisecond timer for this simulation. So if you plan to use this in a real production video game, you should be kind of aware of performance, but if this is a crucial part of some other visual effect, you probably can get some really good results in less than 1 millisecond. Otherwise, if you plan to use it as part of a cutscene or some pre-rendered cinematic or visual effect, you probably can use really large numbers before your system gets out of memory. These neighbor grids are still pretty performant. But that is gonna be all for this video. I hope you guys enjoyed it, and if you did, please consider giving a like and subscribe and clicking that notification button if you like the content and want to see more like it. See you next time.